Okay, guys, this is the last session for one-dimensional motion. This session, I'm going to finish our discussion and this topic on free falling. What is free fall? Actually, when you throw or release something on the gravity field of Earth, let's say this is Earth, you want to, for example, you are standing on a building like this, and you release a stone to downwards, for example. The stone is going to, falling freely under the gravity force of the Earth, and its, acceleration would be g, famous as g, and it is 9.8 meter per second squared. All right. So I don't want to waste the time. I want to solve a example with this so that the you know topic would be more obvious for you. So let's get on with an example. Imagine that I'm standing on a building, on the edge of a building. It is ground. Its height is something like this. 40 meter. Okay, I'm standing here. I want to throw a ball upward with the initial velocity as 10 meter per second. Okay, so I want to first know that how far this ball would go up. So I want to know about its displacement upward. Okay, how much it goes up. And as you know, the ball, when it goes up, it will stand somewhere here, then it's coming down, right? So what is this highest point? I want to know this delta x. I can use this equation. 2 times a times delta x equals vf squared minus vi squared. As you know that, as I said now, vf is 0. My final velocity is 0. I'm down, up here. Okay, so this is 0. What about this one? This is 100. So it becomes minus 100. On the other hand, here, this acceleration, because we are going upward, this acceleration is downward. So the sign of it would be minus 9.8. So delta x equals minus 100 over minus 2 times 9.8. Okay, becomes something like this, 5 meter. Okay, 5.1 actually, but well, let's neglect that point 1. Uh, so this is the height that it reach, that my ball reach there. Um, then I want to know what would be the speed when the ball would go up and coming down before hitting the earth. So I want to know the VF here before hitting the earth minus VI squared, equals again 2 times G times delta X. Here we know again that this VI is actually 0 because the ball would go up here, stand for a moment, so it means that VI is 0. Then it starts to coming down under the force of the earth with the acceleration g equals 9.8. So for the rest of the equation, so it becomes vf, I want to know it later, 2 times 9.8 times 40 as a height of the building plus 5 as the height that it goes up. Remember? Yeah. So it becomes uh, around, let's say, 883, or let's say 4, almost this, um, meter per second squared. Okay? And then if you take the root square from both sides, Vf equals to around 30 meter per second. That's it. That's the speed that when it goes down before hitting the earth, before hitting the ground. Okay? Now I want to know about the time that it takes to do these processes. Okay? About the time, how much time it takes. So here, as you can see, when it's going down, going up, it takes, for example, uh, t1 as a time. Okay. When it's coming down again, down to here, that it has been thrown away, it is t2. Okay. As you shoot now from now on, t1 equals t2. It means that when you threw a ball upward, the time that it takes to go to the highest point equals to the time that it takes that the ball come down from the highest point to the point that it has been thrown. Okay? This is really important. So T1 equals T2, and then for the rest of the motion, it's coming down from the edge of the building to the ground. Okay? To the ground, it is T3. For the first part, I want to use this equation, delta x equals half a t squared plus vi t. I want to call it t1 because it is t1. Okay, and you know that delta x is 5.1, let's say. I want to be more accurate. And half of minus g. This is really important because, this is downward. I mean, here in this equation, it is important that you should consider the sign of this acceleration and the sign of this velocity. They are in the same direction or not, and one of them must be minus arbitrarily. The other must be, for example, positive if they are not in the same direction. Here, for example, I'm throwing up, so the g, the acceleration is downward, the velocity is upward. Okay, so the velocity, I want to consider it positive, and the acceleration would be negative. You can also consider it vice versa, is at your will. So if you write it like this, then you will obtain, and if you solve it, you will obtain 1.02 second. Okay, let's say 1 second. And T2, as we said, again, it's the same as T1, okay, which is 1 second. What about T3? T3, the ball have, again here, uh, let's say an initial, in this process coming from here down to here, it has initial speed vi, and this initial speed is actually 10 meter per second, as the same as we throw it away from here with this initial velocity. So it's going up, stop here, then coming down to here. The velocity would be the same, but in the different direction, as you can see. It was here upward, then here downward. For T3, I want to again solve this equation, delta x, which is 40 meter, the height of the building, equals half of a t squared plus vi t. As you know, I said here, the initial velocity and the acceleration is in the same direction, downward. So they must have the same sign. So if I consider, for example, the velocity or acceleration positive, they must be, both of them, they must be positive. Otherwise, both of them, they must be negative. I want to consider it positive, as it is more user friendly. So, and then if you solve this, sorry, I want to call it T3. T3. If you solve this, it's gonna be around 2 seconds. Okay, 2 seconds. So the total time it takes, the whole process, it takes this time, 4 seconds almost. So that's it. That was a great example we solved, and yeah, I think all the question in this area would be the same as like this. See you soon later. Bye.